So I'm going to present some results of experiments and numerical simulations for the release of massive grains onto an erodible layer of the same material. And this will be applicable, hopefully, to a range of geophysical flows, such as the snow avalanche that's shown here. Our experimental setup is an inclined plane, which is made rough by attaching a layer of glass beads. And before the experiments, we prepare an erodible layer by letting a flow of carborundum grains, which we're using for these experiments, to flow out and leave a uniform static layer. And then we place a cylinder of the same grains on top of that layer and release it. And this will form avalanches as it propagates downslope. And the behavior of that avalanche will depend on the thickness of the erodible layer and the slope angle. So, firstly, for shallow slope angles, we get an avalanche which propagates some distance downslope and then decays and comes to rest. So here at the end of the experiment, it's stopped and everything has been deposited at a thickness which is greater than the initial layer. For the next set of experiments, we prepare an erodible layer at a similar angle, but then before we start the experiment, we increase the slope angle slightly without disturbing that layer, and it still remains static. And this gives an abundance of material for the avalanche to erode. And so in this case, as the avalanche propagates downslope, you'll see that it grows in width and in thickness, and it continually erodes more mass from the erodible layer than it deposits, so it continues to grow. And the final case is steady avalanches, where there's an apparent perfect balance between the erosion and deposition, so the avalanche remains in a constant width and thickness as it moves down slope. So we're limited obviously by the length of our experimental plane here, but as far as we can tell, this is an apparent steady motion, which if you're able to find the perfect conditions between the balance of erosion and deposition for certain slope angles, we can get an apparently steady avalanche which will propagate for large distances. To model these flows, we use a depth-averaged shallow water type avalanche model. So we have averaged the velocities through the thickness of the flow, which reduces the problem to two spatial dimensions. So we have mass and momentum conservation equations, and our source terms consist of a balance between gravity and which is opposed by the basal friction. And we have viscous terms which come from the depth-averaged mu of virology, where the coefficient of viscosity is fully determined by the friction parameters, which I'll talk about next. So our friction law is based on the work of Olivier. And to measure the parameters for our setup, you have to perform a few experiments. First of all, we measure the thickness of a deposit that's left by a steady uniform flow, which we call h-stop, for different slope angles. And for this h-stop, you then incline the slope and record the greater angle before this flow begins to flow spontaneously, which is called h-start. And if you get these two curves, you have a range of friction angle parameters. And secondly, we measure the Froude number versus the thickness for steady uniform flows, which is this figure. And this gives you a steady uniform flow rule, which gives you the remainder of the parameters that you need. For our case, we have angular particles, and we find that there's an offset in the flow rule. denoted by gamma here. So this is for our setup, and this offset is not present for glass beads, which is here. This makes the friction law that we need a bit more complicated. So we have a new friction law, which is very much based on Olivier's work, as I said, but there's an added complexity coming in from this offset. Essentially, we find that we need to transition from a steady to an intermediate flowing regime at a Froude number which is different to beta that you would normally transition. And we need to do this to ensure that from our numerics we have a deposit layers which match that H stop value. This just adds some added complexity into this intermediate friction regime, where the dynamic friction is from the steady uniform flow rule, static friction and intermediate is an extrapolation between those two. And this is just a slightly more complicated form of Pelucano-Forte's extended friction law for dynamic, static and intermediate regimes. So now we can solve. We have all the parameters. So our numerical simulations. We replicate the experimental conditions exactly. And in this, so firstly for the shallow slope angle, we have decaying avalanches, and the shaded regions here just indicate any non-zero velocities. So you can see that the avalanche propagates some distance before coming to rest, as we saw in the experiment. Again, for the growing avalanches, we see that the width and the thickness continually increase. And finally, for the steady avalanches, again, we're able to reproduce the width remaining constant downslope. So we have this apparent steady propagation. Finally, to come around to the title of the talk, which is where we are going to talk just very brief. Oh no, one more slide. Okay, so here are cross slope profiles for each of those three different behaviors. So we've taken a slice, again, the cross slope direction of the plane, looking at these deposits. So you can see for the decaying avalanche, everything has been deposited above the initial layer thickness, which is why it loses mass and comes to rest. The growing avalanche has eroded a trough from the static layer, so it's gained mass. And the steady avalanche, you can see a kind of perfect balance between these levées and a small trough that's been eroded. So coming on to the segregation, we can use a segregation theory which is normally applied for dispersed mixtures, where it's powerful even in this depth average model to do problems such as fingering, where a steady uniform flow breaks down into fingers as it moves down slope. So this, as I said, this theory assumes instantaneous segregation between small and large particles, where a layer of large particles is segregated on top of a layer of small. And we want to apply this now to our flow to visualize what happens in the erosion deposition process of the avalanche. So we've gone on to do some further experiments using different coloured sand. So we now release from a cylinder yellow sand onto an erodible layer of red sand, but the friction properties are exactly the same. We just want to visualize what happens to the original release of this yellow sand and where it ends up. So we're applying the segregation theory now. We assume that there's a layer of yellow particles on top of a layer of red particles rather than large and small. So just looking at the steady experiment, but using this red and yellow sand, we can see that the avalanche remains steady as before, but most of the initial yellow sand, by the end of the plane, has all been deposited, which means that the avalanche, while it maintains a steady state by eroding and depositing in a perfect balance, the the initial grain from the cylinder are actually left behind, and it's entrained new, more red particles from the base. And so we can do this with the simulations as well, just using this simple segregation theory. And again, we can see the same results where the yellow particles are deposited, and near the end of the plane, we're just left with the red. That's all.
That's all. There's time for quick questions.
I mean, some of you have kind of different types of solutions. Some look very much like traveling waves. Does it make sense to explicitly look for them and see which parameter regimes they exist or don't exist, or do some kind of application?
We haven't done a parameter study, but we have put the solutions into a periodic box, into a travelling frame, and we found that the steady avalanche remains there for at least 20 seconds or more, so it really is steady. Yeah.
And nothing happened upstream in those avalanches?
Upstream of the avalanche?
No, of the...
From... it could, depending on... if there was a thicker initial layer, there could be some upstream movement. Not for these.
Okay, thank you.
Okay, brilliant. So I just want to start by briefly trying to convince you guys that Continuum is appropriate model for granular materials. So these are 3 different experiments from our lab in Manchester that exhibit flow properties similar to classical fluids. So you've potentially got jumps and shocks, smooth variation of your free surfaces, and also wave-like phenomena. Okay, so just to start, I'll briefly go over some notation. So the kind of goal is to develop a continuum model that describes the evolution of the velocity vector u, but also for granular materials, we're interested in the local solids volume fraction phi, which is the amount of particulate material at a point compared to the total volume. And so we're going to be describing the deformations of our granular material with a strain rate tensor d, and I'm going to use this double vertical bar notation to denote the second invariant of any of the tensors that we're going to be interested in. Okay, so straight into it, we've got this very now famous and popular model for granular flow known as the mu of I rheology, and that's really a generalization of the Coulomb idea that greater tangential force is always accompanied with greater normal force, and they are proportional through a friction coefficient mu. But in our tensorial world, this is really relating the magnitude of a shear stress tensor tau to the pressure. And the mu of I rheology postulates that the friction coefficient actually depends on this inertial number I, which is a non-dimensional strain rate, and that is also bringing in dependence on the intrinsic grain diameter d and also the density rho star. And a big assumption made with this model is that the material is incompressible, so the volume fraction phi is a constant and our velocities are divergence free. Okay, so the kind of gist of my work is to use this kind of mathematical idea of ill-posedness versus well-posedness to analyze this rheology, but also other models for granular materials. And so the idea here is that we conduct a linear stability analysis of the equations to isolate the behavior of these kind of normal mode perturbations. So these are small perturbations of the flow that are characterized by a wave vector k and a growth rate lambda. And we're going to say that the equations are linearly well-posed if, in the limit that this wave vector tends to infinity, the magnitude of it tends to infinity, the growth rates remain bounded. Okay, so if the opposite is true, then the equations are ill-posed. And ill-posed equations have, very difficult properties, but they're also not very physically realistic. So this high wave number limit is actually corresponding to very, very short wavelengths. So if I'm doing an experiment in my lab and there's a high frequency alarm going off somewhere in the department, then that constitutes a very low amplitude, but also a very low small wavelength perturbation. And I don't expect that to come to dominate the dynamics of my flow. And so that's, the kind of physical basis of why we're interested in ill-posedness and well-posedness. So applying this to the mu of I rheology and the kind of typical functional form that we see that's proposed by Jokfotet and Poulican, we see there's a large range of inertial numbers in which the rheology gives well-posed dynamic equations, but when the inertial number is very small and very large, denoted by these white regions here and here, then the equations are ill-posed. Okay, so I'll just demonstrate the kind of things that happen when you go into these ill-posed regimes. So this is a simulation of a chute flow at a high inclination angle. So that's pushing us into these large inertial number regime, and you see that very quickly we get a spontaneous formation of these short wavelength perturbations in the flow, and they really come to dominate quite quickly. There's exponential growth, and at some point that actually breaks my simulation. I have non-convergence in my numerical scheme. There are some natural singularities in the equations in any case, so we have finite time blow-up of the equations. And another kind of very unphysical property of ill-posed problems is that the results of numerical computations actually depend on the grid I'm using. And so this is another simulation. This is now a decelerating flow, and these are some perturbations that I see in close to the base of the flow, and the inertial number now is quite small. And this was quite nice when we first saw this, because this looks very similar to force chains that we see in actual experiments that transmit the forces between grains and maybe also shear banding. But the issue is with ill-posed problems that when you refine your mesh, I now have twice as many grid points in each direction. I actually get a lot more of these features. The width of the features is a lot thinner, and the magnitude of the strain rates and the inertial numbers along these shear bands is actually a lot higher. And so actually this is not a physically realistic instability. It is completely generated from the numerical noise in my computation. Okay, so what do we do to get well-posed equations? Well, we found 3 different strategies that are all quite distinct, and you've heard about one already, and that is to assume that the flow is very shallow, and this leads to equations that are very similar to the shallow water equations, and they're well-posed and depth average, so I won't discuss those here. But the other 2 strategies that I will discuss are that we can just simply modify the mu of I relation. And so that curve you saw before that had issues at small and large inertial number will just change the functional form, so that keeps the structure of the equations. But then the more drastic approach is to relax this incompressibility constraint, allow variations in the local solids volume fraction, and so develop a compressible theory. So this is now a new functional form for the mu of I relation. Now it's on a semi-logarithmic plot, and you see the limits of the old rheology, where the old rheology came ill-posed, and now we can actually go down all the way to inertial number is 0 if we choose a curve that has the appropriate functional form down here, and the same when we go to large inertial numbers. But we actually find that there's always a maximum inertial number in which, above which you can't form well-posed incompressible theories, just using this very simple incompressible mu of I rheology. Okay, so when I go back and put this new curve into my numerical computations, I find a numerically stable result that's completely grid resolved, and we have this nice uniform value of the inertial number that now corresponds to a very slow creeping flow towards the base of my chute flow. Okay, so just to finish, I'll go over our new idea for compressible theories, and now this is a very general theory that we call the compressible I-dependent rheology, or CIDR. And so this actually encompasses not only the mu of I rheology potentially, but also ideas from critical state soil mechanics. And what we've done is we've generalized this stress tensor now, and saying that the magnitude of the stress tensor now not only can depend on the pressure in the inertial number, but will also depend on the packing density of the grains, because material with closer packing is going to be stronger than material that's packed less densely. Okay, so now that we've got divergence of U is no longer 0, we have to switch to using a deviatoric strain rate tensor as well, and we actually have to model the evolution now of the of the divergence of the velocity. And so this is very similar to in critical state solid mechanics. You have a flow rule, and it's also very similar to Reynolds' theory of dilatancy, in which volumetric changes come from shearing material. And so we're linking now the volumetric changes to the shearing through a very general dilatancy function f, which again can depend on the pressure, the inertial number, and also the packing of the grains. Okay? And so one of the nice things about these equations compared to the incompressible equations is that I can actually solve this equation for the pressure. And so now I've formed an equation of state for the pressure, and so unlike with like incompressible Navier-Stokes, I don't need to do some very complicated implicit pressure schemes in order to ensure incompressibility. Everything is now very explicit, and that actually helps a lot in developing simple numerical schemes for these equations. Okay, and so the real big bonus, as well as that, is that we can actually make these equations well posed for all deformations, that's all values of the inertial number, all strain rates, and all packing densities, provided that we choose these new functions, y and f, the yield function and the dilatancy function, to satisfy these criteria. And these criteria come directly from the ill-posedness analysis, this linear stability analysis. But it actually turns out they have some other really important physical properties, like ensuring that every deformation dissipates energy, and every deformation also generates entropy. And so actually the physicists really like these equations as well. So that's everything. I'll take questions.
Questions?
So when you extend your mu of I function, is there only one that works and that gives you everything stable to 0?
No, you've got quite a lot of choices.
And even if you've got lots of choices, how do you make that choice?
So the choice I actually chose is the choice that gives a result that's closest to the old theory, but is remaining well posed. So I actually derived a neutral stability curve and just took a curve just below that. Okay.
I mean, ideally you would have an idea what the real physics is missing. I mean, if a model is ill-posed, there is some physics missing.
Yeah, of course. And so we think one of the important physics is compressibility, but yeah, there's probably other effects that are going to come in as well.
For the two functions in your model, what is the simplest linear function? For example, I know that in the literature you have just those functions just linear in the gap, the critical volume fraction.
Okay.
Are they stable or not stable?
No, they don't trivially satisfy those equations.
Yeah.
You have to do something quite special with the dilatancy function. It turns out, so it's still an open area.
Thank you.
Okay, thank you. Good morning, everyone. And I'm also a PhD student here in Manchester, working with Nico and Chris Johnson. And the story I want to tell you today is about the ability of granular materials to self-channelize when avalanching down a rough inclined plane. So the experimental setup is very similar to what Andrew explained, but we don't have the erodible layer. What we have is that the global dynamics can be divided in mainly 3 stages, where first the front propagates, for high enough fluxes, the front propagates continuously downslope, and these static lateral boundaries form spontaneously just behind the front. Eventually, a steady state is reached where height and velocity profiles don't depend on the downslope position, and if you cease the inflow, the moving channel drains out, leaving behind the fingerprint of this levate channel morphology. However, if we look more closely to the system, this very simple experiment is a playground to study nonlinear phenomena, because we see that in the surface there are some surface instability going on here. If we look towards the margins, there are some erosion deposition process going on that it seems that doesn't affect the steady state behavior. You have this readjustment kind of testing if the system is indeed in the steady state or not. And you see that at some point I will just change the aperture of the funnel here, changing the inflow flux, and the system will spontaneously readjust to the new steady state according to this new controlling parameter, which is the volume flux. One of the biggest motivations to study this self-generalization and the formation of this static boundary that we call the levees, it's because it's widely observed for large-scale geophysical flows, such as pyroclastic flows, snow avalanches, and even debris flows on the surface of the moon or in Mars. And the self-generalization prevents lateral spreading, which can enhance the run-out distance for these flows, and then enhance also the destructive outreach of these flows. Previous experiments have been done, and we know a lot about this system experimentally. So we know that for high enough fluxes, the width of these flows increase linearly with the mass flux. The thickness of the moving channel seems to be insensitive to mass flux, so it's constant for all fluxes. And the surface velocity at the center line, or the maximum surface velocity, increases initially but eventually saturates for high fluxes. We also know that there is a difference when we do the experiment with the spherical beads. The levees are not strong enough, and eventually it spreads out in a very slow process. Whereas if you do with angular particles such as sand, the configuration is stable for even really long times of inflow. So our question here is, how can we model, or can we model this system to have a quantitative agreement with the experiments? So in order to do that, we apply a depth average model in which the system is governed by a mass conservation, and a momentum conservation where you have the inertial terms, pressure forces, a source term where it takes into account gravity and friction, and here is one of the crucial ingredients of the model. In this friction coefficient is where the granular rheology is embedded, and where we have to build up the information that there is a hysteresis in the friction law. So for the same slope angle, depending on the Froude number, the friction, the material will feel different friction, which allow the coexistence of static and moving material at the same slope angle. The other crucial ingredient for the modeling is the viscous-like stress, that it's kind of neglected in many of the avalanche models, but here will be very crucial to set the channel width. And I'm not going in too much details into the math, but I want to mention some characteristics of the steady state. So let's take a look. What do we have if we seek for steady uniaxial solutions? So first, in the steady state, we don't have transverse or cross-slope velocity, V is 0. The thickness inside the moving channel is constant, so H, we call big H. And we recover the equation of motion, it's reduced to a balance between viscous stresses, friction, and gravity. So here is the point where I show you that the viscous stresses is crucial, because if you don't have this term, this balance is just between friction and gravity, and you have, instead of one single solution, you have a family of solutions, and you cannot determine this, the real state. We have our boundary conditions, so we assume no slip and no shear stress at the boundaries, and to close the system, we have this integral constraint which links to the volume flux. Okay, so let's solve the equation numerically, and what we get is that for high enough fluxes, here you have contours of depth average velocity, and here thickness. You have that the front propagates downwards progressively because the flux is high enough, with these lateral boundaries spontaneously formed. And if we look, what we have is like initially, all the width is mobile, everything is moving. Can you hear? When the levee is formed, the velocity profile approaches the steady state solution, which is this exact solution is this white curve here. When the flow is ceased, the channel drains out, leaving behind the fingerprint of this channel levee morphology. If we look to a cross-slope thickness profile, we have this constant thickness. When it's during the drainage, the motion is just in the center of the channel, and you have a deposit, the super elevated levees, which is linked to the thickness of the channel, which then we think that if in the field you measure the height of this deposit in natural flows, you can infer something about the previous motion. Let's now compare with the previous experiment. So what we have, if we compare the lines are the theoretical prediction from the exact solutions, and the data points are taken from Takagi, McEwen, and Huppert, who did the experiment with sand. And what we have is that the thickness is insensitive to mass fluxes, such as observed in the experiment. The width of these flows increases linearly with the mass flux, and the downstream center velocity increases initially and then saturates. So what we learn from this is that effectively increasing the mass flux is more effective in making the channel wider than making the channel faster. You can see that the comparison here for the thickness and width are in much better agreement than the surface velocity, but these have to do with the reconstruction of the 3D of the surface velocity from the depth averaged solution. If we look closely towards low fluxes, we see that the steady solution stops existing. If we look to the thickness here, it's kind of like a folding bifurcation. But what happens in this region? So we just do the same experiment, but with a low mass flux. And we see that the front doesn't have momentum enough to propagate continuously, and it comes to a halt, blocking the flow behind. And then it sends a backward propagating wave until the source, and then grains pile up. The grains pile up until the surface inclination goes beyond the critical angle, and then it fails, triggering this avalanche in like a solitary wave that propagates down to the deposit. And this becomes progressively until in the long time limit, it becomes really periodic, these pulses. The question is, can we model this? So we do the same numerical experiment, but with a lower mass flux. And what we get is that we have this pulsating pattern with the backward propagating wave until the source, and then it fails again with these sending these solitary waves. And if we compute the thickness profile, we get a very similar pattern than in the experiment. So with that, I come to my end, my conclusions, and thank you very much.
Time for questions?
When you look at the velocity profile in the x direction on your which you levies for, it looked like your velocity profile was right from the surface to the top of the. If you look at your velocity profile, in that one there, the velocity profile goes right from the bottom of the levee to the top surface. But then when you were doing your modelling, it looked like most of the flow occurred in the top of the levee and not down at the bottom.
Well, if you're mentioning the variation of the velocity with the depth,
Yeah.
here we don't have the information if the whole material is moving or if there is a deposit layer, a static layer underneath.
Okay.
But with the depth averaged model, we cannot reconstruct this, and that's an open question that we don't know now.
So you don't know how thick that static layer is at the bottom of the levee.
We don't know if it's all moving or if there is this static layer and then it starts moving.
Okay, thank you.
Thank you. I'm a new lecturer at Ritvat University. Today I'm going to talk about modeling of gas-solid flows with turbocharging. I started this project when I was at Princeton University, so these are my colleagues, Dr. Kolehmanen and Professor Sankaran Sundaresan. So briefly, what is turbocharging actually? Turbocharging is observed in everyday circumstances, such as when you rub a balloon against your wool sweater, they pick up charges and they tend to stick each other. And also turbocharging is naturally observed. Here I'm showing you one photo from Mars. We can see there is a sunstorms and there are lightnings. These are because of this turbocharging. These particles, it's a dry environment, they pick up charges very easily. And another example here, it's an eruption in Mexico. And we can see in the plum over the eruption, there are lightnings due to this turbocharging. So, and there are also some significant industrial implications. For example, here there was a silo before. Here, the application, they were transporting the explosive powder. They contact each other, they pick up charges, and there was an explosion. So our research question is the connection between the macroscopic behavior of the flow and the turbocharging is poorly understood due to the complex nature of these physics. So our research question is how turbocharging affects the flow behavior and flow behavior how affects the turbocharging. So this is our flow configuration. It is much simpler than the example I just showed in my previous slides. Here is a fluidized bed. What is fluidized bed? We have a vessel and we pour the particles in this vessel and we inject the gas at the bottom. If we increase the gas velocity at the bottom, the particles get agitated and they leave solid state and they behave like a fluid. So in this bed, this is really small. It is 1 centimeter with square section. These particles are polyethylene, dielectric material with diameter of 250 micron. The bed walls are glass, and we use nitrogen as a fluidization gas. And these experiments were conducted at Tampere University of Technology, Finland. So here I'm showing 2 videos, actually. The left one is we conduct this experiment at a low humidity level, and the right one we conduct the experiment at high humidity level. So we can see there is a significant difference between the flow behavior. Here we can see slugging of the particles. Particles are really highly agitated here. When we look at here, we have a kind of static bed, and we have only few particles at the freeboard. So we think that we can attribute these fluidization characteristics based on the humidity. So we would like to, we want to model this flow. So what we developed earlier Lagrange approach, or namely CFD-DM. In this approach, we solve local average continuum equation for fluid phase in earlier field, and we track particles by Lagrangian approach. In Lagrangian approach, we solve Newton's equation of motion, and we couple these phases through interface momentum transfer, including pressure gradient and drag force. And we also track the particle collisions. So we use soft sphere model. It means that the collision is kind of taking time. It's instantaneous, so we resolve the overlapping of the particles. And these particles also, they carry charges, and we have a turbocharging model, the charge for charge rate, transfer rate, and also we solve Poisson solver to compute the electric field. So this is a kind of mesoscale modeling. The main advantage is we can easily observe the agglomerate and break off the particles. So this is our charge transfer model. There are 2 particles here, Q1, Q2, and the charge rate between them given by this equation. In this equation, one parameter is overlapping distance. Here there is a Heaviside function. It means that we will take into account of charge transfer when the particles approaching each other during the collision. And we have another parameter, this is the work function. So what is work function? Actually, work function is kind of solid state physics. The minimum energy need to pick up 1 electron from your material to in a vacuum. So we use here effective work function because we would like to use this one for the dielectric materials also. This is a lump parameter. We use our experimental data to determine it, or we use some quantum mechanics calculations. And here also the third parameter is the electric field. And what we found when we working on this one, we need a kind of good solver. We need to accurately predict electric field at the contact point. So we developed particle-particle mesh type finite volume approach. So what's this approach actually? In this one, we decompose electric field into two parts, with the long range one and the short range electric field. For long range electric field, we solve Poisson equation. Here, this is the electric potential. Here, the charge density. And then for short range interaction, we just use truncated pair sum. So finally, we have a total electric field which is short range, long range, and we have a correction to avoid double counting. And finally, we can compute the electrostatic force on the particle using the electric field and the charge. So we want to validate our approach, so we just started a really simple experimental study. This is vibrated bed. It is just simple cup. We put the particles in the cup and we vibrate them for a while. Then we put in the Faraday cup and we just measure the total charge. So before presenting my results, I would like to just briefly go through my some definitions. It will help for the discussion, I think. We say that equilibrium charge, it is the charge, the maximum charge the particle can pick up if there is no electric field. So if there is electric field or the multi-particle system, then the charge is saturated. It's given by Q infinity. If there is no electric field, then these are equal each other. So then we also characterize the electrostatic force based on this dimensions number, which is the ratio between the electrostatic force and the gravity, the weight. So this is our first result. This one, the first graph shows the total charge versus mass. In this experimental study, we keep the humidity level constant and we vary the mass, or we keep the mass constant or vary the humidity. So this first figure shows the total charge versus mass in the system at a constant humidity. As we can see, there's a nonlinear behavior. We find this interesting because it means that there is a charging mechanism that depends on the multi-particle system. And when we look at the second figure, it is the charge versus the humidity level at a constant mass. And we can see as we increase the humidity level, the charge, the absolute charge decreases. These results are consistent with the previous experimental studies. And then we perform our numerical simulation of this system. Here, this is the charge ratio, Q infinity, Q equilibrium for versus mass at a constant humidity level. The dots here refer to experimental results, and the line is our simulation results. As we can see, we can very well capture the nonlinear behavior, and also we have a good agreement with the experimental study. And we can see there are some discrepancies for really small mass, but this is really difficult to measure charge when you have really little amount of particle. So then we went back to our original case, fluidization 1. So we just take a close look what's going on in this the case with the low humidity level. When we look at here, we can see that there are multi-layer multi-layer formation of the particles at the wall. Actually, it's a minus, plus, minus, plus. So then we perform this. We use our numerical approach to perform this simulation, and this is our. And we also measure the pressure drop in our system. So this graph shows the scale pressure drop versus mass in the system, and here blue dots the experimental data. Here we scale the pressure with the case without charge. It means that here the pressure drop, all balance the total weight of the system. When the charge increases in our system, the particles stuck at the wall, and the total weight, it is more or less balanced with the wall and the bottom. So the sad thing about these results, we have a good agreement for small charge cases, but we have kind of discrepancy for high charge cases. So when we take a look in our numerical simulation, we saw that we couldn't predict this multi-layer formation at the wall. So if I summarize what we have done, we developed a robust, reliable CFDM approach for gas-solid flows with turbocharging. And charge transfer, we have one lump parameter, and we've determined it using our experimental study. And we performed two cases. One is the vibrated wet. The results are really good agreement. For fluidization case, we have some discrepancies. We are still working on it. So for current and future research, We assume that the charge is located at the center of the particle. For dielectric material, there will also the charge distribution over the particle. So it's called polarization. So we perform the vertical channel with polarization effect, with polarization and without polarization. In this case, it is the standard one which has no charge, no polarization. So we can see this kind of the channel flow. When we include electrostatic forces, we have a meandering flow, and if we introduce polarization, we have just only sheeting of the particle. The point is here, if you take into account the polarization, you will get completely different behavior. So thank you for your attention.
Question? Yes?
Just on the last slide, I just didn't understand the meandering flow.
Actually, here the electrostatic energy, it is getting minimization. So particles get charged, so they try to minimize the electrostatic energy. So this is the reason they have this kind of meandering. They would like to get closer to each other.
The vibration density does not change?
Vibration density, you mean?
In your experiments, or you have vibration?
No, this is more or less constant, yeah. This is the reason we use nitrogen, actually.
Okay. Thank you.
Thanks.
Hi, so I'm a PhD student here in Manchester with Nico Gray and Chris Johnson, and I'd like to talk to you about the work we've been doing on the retrogressive failure of a layer of granular material. By this retrogressive failure, what we mean is this upwards propagating erosion wave that you can visualize on this video of the sand dune here, that starts off by a perturbation of people walking on the sand dune near the bottom, which causes the layer to start flowing. And this wave propagates upwards, eroding all the material that was static above this and causing it to flow downstream. And in our lab in Manchester, if I can get the video working, we're able to reproduce this experiment. So we can create a layer and then perturb this layer when it's in its metastable state. That again causes this nice upwards propagating erosion wave. That it ends up eroding all of the material above it that was static and causes it to flow downstream. So the experimental setup for this is we have the... We incline the slope at a certain angle, say zeta naught, and then we can create a steady uniform flow from a hopper that leaves behind a layer that we know the thickness of, this H-stop layer. And then it turns out if you gently increase this angle slowly, this layer can exist in a metastable state due to the hysteresis. And then when you perturb this layer, then we can create this upwards propagating avalanche. And in the video that you could see before, they had some nice waves there, but for the moment we're just purely going to focus on the upwards propagating avalanche, just for time reasons in this talk and the difficulty in modelling this instability downstream. So this is the geometry we're going to use for this model. So we're going to say initially we have a static layer of given things H naught, so it's zero velocities in the static region. That's somewhere in between these, this H stop that was the original thickness we created it at before inclining the angle. And then downslope we're going to have a steady uniform flow of thickness H infinity and depth average velocity U infinity. So then in order to model both the static material and flow material at the same time, we're going to have to use a hysteretic friction law. So let's look at what equations we're going to use. We're going to use the shallow water avalanche equations that have been mentioned a couple of times already, where we have the mass balance and a momentum balance equation, where here we're going to have the H is avalanche thickness, U bar is this depth average downslope velocity. These are just like the shallow water equations, apart from this added source term on the right-hand side here, which is a balance of gravity trying to pull the grains down the slope and friction keeping them where they are. But it turns out this friction coefficient here can't just be the standard Coulomb one. It has to depend on the flow thickness and the Froude number, which is like a non-dimensional velocity. So this is the hysteretic basic friction law we're going to look at. So it's based on the work of Olivier, as Andy mentioned earlier. So where they had this dynamic regime, which is like here, which came from the flow rule, and lots of people have verified this in the past. There's been lots of different experiments on here, And then when the grains are static, you've got you just need enough friction to be able to balance all the forces that are trying to pull the grains down the slope. And in between this, you need this intermediate regime. The key thing here is this increase in friction with the decrease in velocity. And in this region here, Olivier, they just did like an exponential fit due to lack of experimental data in this region. So this is the flow rule data that was taken from one of Olivier's papers, and we're using glass beads here. And they, the original formulation of extended friction law was to say at the thickness h stop, there is a transition at the fluid number beta down here, but you can see there are no experimental data points here. So where we get this increased transition at this beta star value here into the intermediate regime comes from the minimum steady uniform flow that you're able to observe in these experiments and has a thickness h star corresponding to it. So if we just plot like contours of this source term here, so the solid black line is the fact where the source term is 0, and if you're above this line, anyway, all the grains want to accelerate until they reach a steady uniform flow on this side. If you're below this in the white region, they all want to decelerate. And the region that becomes key for modeling these retrogressive failures is this white region here. So you can have static layers that, to very small perturbations, are stable, but if you give them a larger perturbation, they'll be able to flow. So if we go back to the lab now, we can perform these experiments, and if you have a high-speed camera lined up down the center of this shoe and you take a sequence of images, you can take the middle column of these pixels and line them up so you can have time going along this axis here, and the distance where the top of the chute's here and the bottom of the chute's there on this axis. So if you look at this now, all these horizontal lines here represent the initial static material. The blurred region here is the moving grains, and then all these lines with negative gradient here are all the erosion deposition waves you see downstream. And they are erosion deposition waves because the regions of static material in between them, as you can visualize on this plot. This line here is the visual retrogressive eroding wave propagating upslope, and you can see it's a line of constant gradient, which suggests we can look for traveling wave solutions, and we can also take the gradient of this line to find out the velocity of this wave propagating upslope. So if we know, because we're suggesting we can look for the traveling waves, we can transform into a frame that's moving with the wave, which changes the mass and momentum balance equations to the ones on the slide here. And if we integrate mass balance subject to knowing that initially we've got a static layer of thickness h0 that's got 0 velocity, we can find that everywhere the velocity and thickness everywhere are related by this constant. And then we can rewrite the momentum balance equation here now as this ODE, which we can then say go into MATLAB and create solutions. So these are all for the same final inclination angle, but we created different layers of initial thicknesses to start with. And you can see that provided you don't go above h start, where the material will start spontaneously flowing by itself, and you're in a region where there is a steady uniform flow for it to connect onto downstream, you can get a whole series of these solutions. So if we go back into the lab, we perform a whole series of experiments. So these are all, we created an initial layer at an angle of 24 degrees. We could measure its thickness, and then we just progressively increase these layers by different amounts. So initially, if you increase the layer by half a degree or 1 degree, the layer is too stable. So when you perturb it at the bottom, there isn't this upwards propagating erosion wave. And then as you go beyond this, you would get these whole series of waves that you can measure, and then if you try to go above zeta start on this side, you couldn't have the layer static there, but it's already flowing. We can see that the theory that we have is able to quickly predict this increase in the wave speed with increase in the angle, the change in angle, and get the magnitude very close to these solutions. And this is just to show that we can perform these experiments at different regions of parameter space, and again we get a very good agreement with the existence of where these solutions exist and not, and the increase in the wave speed with the slope angles. And then this plot here is like we can go through the equations and we can find the minimum thickness of the initial layer that we need at each angle for one of these retrogressive solutions to be able to exist. And you can see there's a really good agreement here between The dots, which were all, we've seen all these retrogressive wave solutions, and the crosses where the layer was too stable for these to exist. And we can see here that the solid black line, which is theoretical prediction for the boundary between these solutions existing and not, is a really good match for with all the experimental data we've got so far on this curve. So it seems like we're doing we're very promising with what we do and be able to predict these retrogressive solutions very well. So the conclusion we've seen that in nature and in our lab we can see there's these retrogressive solutions exist, and the shallow water modelling is able to capture the existence and the velocity of these upwards propagating erosion waves. But the main difference between this sand dune video that you can see here and our experimental lab work is that in the lab because we've got a fixed base that we've made rough, we set the depth, the maximum depth of the erodible material, whereas in the sand dune, like potentially there's potentially the whole depth of this is erodible. So what sets the depth of this flowing layer is something that we need to work on and look at in the future. So yeah, thank you.
Question?
Yeah.
Well, I mean, in this picture, you clearly see that the thing breaks out to the left, right? So
Yes, it does. Yeah.
is that correlated with the surface of the dune, or is there a kind of a cascading effect that this is a perturbation for the next portion?
We've not done any of the dune work ourselves. It was just a video we found on YouTube. So it could just be there is like I don't know, some like initial fracture or a weakness in the material at that point that just causes it to flow.
The questions? Yeah.
Just on the comparison between the theory and the experiments.
Yeah. Oops.
So it's a bit of a reach.
This one or that one?
No, the one afterwards.
This one, yep.
There are a few dots either way on the wrong side. Do you have any feeling for what's missing? Is that within the experimental error?
It's probably within the experimental error because the inclinometer that we have has got a max, it's like 0.1 precision, but in reality it's probably larger than that. So it's within experimental error, I'd say, where these are, because that was probably just to the left and that was just to the right. So there's going to be an error in the thickness we can measure with our laser and an error in the actual angle that the slope is from the inclinometer.
And there was also an old study by Daher and
Daher and Douadi,
so not exactly the same, it's just local perturbation to see if you can go upstream or downstream. Does it compare well with this line also?
So they use a different way of making the bed rough. So their existence, these solutions, I think touches H stat at some point. But you see with different parameters, this line where these solutions exist can move around. So, yeah.
Okay, thank you again.
Thank you.
Okay, hi, I'm Caitlin from the University of Leeds, and I'm talking about a numerical method called stress particle SPH with an application to landslide behavior. So we're interested in two stages of landslide behavior. These are the landslide initiation and the propagation. So landslides initiate when a mass of material on a slope fails, and this usually occurs when an area of the material is weakened due to some external force, and it undergoes irreversible deformations. This area and these irreversible deformations are localized and spread to form a failure surface, and the mass of material fails along this surface, and a mixture of soil, rocks and water propagate as a fluid then. And it's important to model both of these stages for risk mitigation purposes, and these stages exhibit solid and fluid behavior, so modeling them both with the same numerical model can be quite difficult. So one numerical model that is appropriate to model these types of flows that exhibit a large deformation is smoothed particle hydrodynamics, or SPH. So SPH is a meshless method where the system of equations are discretized with a set of particles rather than a mesh. So the function values on each particle are approximated by summing over the surrounding particles and smoothing over them with a smoothing function called a kernel. But like most numerical methods, SPH has some numerical instability. And one of these, which is relevant to the current application, is this instability called the tensile instability. And it occurs in materials that have a strength when they're subjected to a tensile state of stress, so when they're being pulled apart. And what happens is, instead of being pulled, they tend to form clumps, which then causes this non-physical fracturing that is clearly seen in this problem here, which manifests itself quite early on. And this problem is the dam break collapse of a granular material with a cohesive strength, so this is of interest here. So one way in which to stabilize the scheme is to have another set of particles and distribute the function values over both sets of particles. So here this method is called stress particle SPH, and you store the velocity on one set of particles, which are called the SPH nodes, which are denoted by the circles here. And the stresses are stored and updated on the other set of particles, which are called the stress points, which are the crosses in the diagram. So this way of splitting up the equations and like staggering the system is commonly used in grid-based methods, but it has limited applications within SPH. And so far, all its current applications are restricted to problems that don't exhibit a large displacement, and it's never been applied to the problems that I'm interested in. So to describe landslide behavior, I'm modeling the material as a soil that has a time-dependent stress, and we can split up the total deformations of the soil into an elastic and a plastic part. And we introduce a yield function, which is a function of the stress state, such that when the yield function is below a critical value, all the deformations in the soil are elastic and therefore reversible. But when the yield function is above a critical value, the deformations are plastic and irreversible damage has occurd. So here we use a Drucker-Prager yield surface, which is just a function of the principal stresses, and the key parameters involved are the cohesion and the internal friction of the material. So just to summarize the main governing equations, you have the conservation of momentum and the rheological equation. And these can be rewritten here as the time derivative of velocity, which is just a function of the stress, and the time derivative of the stress is a function of the velocity, which comes from the total deformations of the material, and the stress, which comes from the plastic deformations, where you introduce a flow rule. So in the stress particle SPH, we solve the momentum equation on the SPH nodes using stress information from the surrounding stress points. And we solve the rheological equation on the stress points using the velocity information from the surrounding nodes. So one key factor to consider is how to distribute the stress points and also how to update their positions, because the velocity isn't stored here. So one way, which I've named the inside approach, is to have a number of stress points inside 4 neighboring nodes, and you interpolate the velocity from the surrounding nodes onto the stress points and update the positions of both of the sets of particles just according to the displacement equation. And an alternative option is to have each node has a number of stress points assigned to that node, which I've named the outside approach, and you only update the position of the nodes according to their velocities, and the stress points follow that node at the same distance throughout the entire simulation. So now just to look at some results. These are results from a triaxial test, which is an experimental method within geotechnical engineering where a force is applied to a sample of soil and its behavior is observed, and you can get properties of the soil upon failure. And at the end of the test, the soil sample has these areas of localized plastic deformations, which are shear bands. And the SPH results are shown here for standard SPH, where no stabilizing scheme has been used, and this stress particle SPH with the stress points inside the 4 nodes, the inside approach. And with the stress points, the expected behavior of the sample is observed, but without any stabilizing scheme, standard SPH isn't capable of modeling this type of behavior due to the tensile instability and also other instabilities which I haven't spoken about. So the next example that I looked at was the dam break of the cohesive material, which I showed at the beginning, where you get the fracturing in the material due to the tensile instability. And again, this is the inside approach. And when you have the stress points, this instability the effects of the instability have been almost completely eliminated. So these problems that I spoke about were mainly relevant to landslide failure mechanisms, but then I also wanted to test the numerical method to apply it to situations that are more representative of landslide propagation, because having the stress points and the nodes, that's never been applied to flow type problems, so problems that behave as a fluid. So this problem is the same as the one I just described, except that whereas that material had cohesion, this material doesn't have any cohesion. So this just basically is a sand, and it has a much larger runout, reaches higher velocities than the previous example. So these are just the results of standard SPH, the time evolution of the material. And when I modeled this problem with having the stress points inside the 4 nodes, the runout distance was severely underestimated by the stress particle method. And that's because this method of updating the position of the stress points is insufficient in areas where there's a high velocity to ensure that you always have enough interpolation points for the velocities and vice versa for the stresses on the stress points. But when you use the outside approach, you no longer have this problem because there are always enough stress points for the nodes and always enough nodes for the stress points because they follow each other throughout the simulation. And now the free surface profiles of the case of no cohesion coincide well from the stress particle method with the results from the literature. And also, just to show that having the stress points outside is also still able to solve the tensile instability seen in the case with cohesion. So just to conclude, SPH is a really useful numerical tool for solving problems involving large deformations, which are relevant to both landslide initiation and propagation. But there are some instabilities that you see in SPH, particularly when trying to model the initiation phase, which exhibits more solid behavior, that can cause severe failure of the problem. But having the stress points in the method can either completely eliminate or reduce these instabilities. And we've extended the method so it's also capable of being applied to flow type problems and the propagation phase of landslides. So it's bridging the gap for a numerical method between landslide initiation and propagation. Thank you.
Time for question? Yes?
In your plastic potential, in your flow rule, you had a plastic potential G.
Yeah.
Could I just ask what G you use?
Yeah, for the first case, I use a non-associated or associated flow rule, and in the associated case, G is just the same as the yield function. So that is what I used for the first case that I showed you, the triaxial test. The second case, I used a non-associated flow rule where G, it was very similar to the form of the yield function, except that it also includes a dilatancy term as well. I can't remember the exact form of that. But it's very similar, apart from it has a dilatancy as well.
And does this new method introduce problems for boundary conditions in SPH?
Yeah, it does actually, but there's a way to kind of switch off the points. So near the boundaries, you can just have standard SPH, and then you can use the stress points away from the boundaries. You can use them near the boundaries, but it does cause some problems, yeah.